buffers. Buffers are any substances or compounds that resist a pH change. So they make it so that there are no large pH changes. So the way that kind of works is when you add an acid, so when you add an acid to a solution and you've got a buffer in it, that buffer is going to take up any extra hydrogen ions, which makes sense, right? Because acids are acidic because they've got lots of hydrogen ions. So if a buffer is taking those up, then our pH isn't going to change. Can you guys guess what happens when you add a base? What the buffer does? Takes up the hydroxide ion, yeah. So a base is basic because there's lots of hydroxide ions floating around in solution. If we get rid of those hydroxide ions, we're not going to become more basic. Okay. So because of that, how it interacts with the hydrogen and hydroxide ions, when you've got a buffer present, pH is either going to change just a very small amount or maybe even not at all. So when the buffer takes up those hydrogen or hydroxide ions, it's binding to them, and that binding is reversible. So that reaction is reversible. They can bind, they can unbind, separate. And we talked about blood having a really consistent pH in our body. And the reason that that's able to happen is because something called hemoglobin in our blood acts as a buffer. And it actually keeps blood between pH of 7.38. I don't have this memorized. You guys don't have to memorize this. And 7.42. So your blood pH changes very, very little, if at all. And that's because hemoglobin is in it and acting as a buffer. Have you guys heard of hemoglobin before? Yeah. Okay. Can I erase this? No? Okay. So most areas in your body have a really similar pH to blood. The only kind of notable exceptions, your stomach has got a way lower pH, is way more acidic than your blood. The vaginal canal has way lower pH, is more acidic than your blood, and your urine is more acidic. And we talked a bit about urine last time because your kidneys are actually filtering out hydrogen ions, right? So those are kind of the notable exceptions, and we'll talk more about pH when we're talking about those systems, so the digestive system and the reproductive system and the urine. Okay, so we're going to talk about neutralization reactions. So in some places in your body, you guys remember neutralization reactions at all from grade 10? No. Or they might have just called them acid-base reactions. Yeah. Yeah, thanks. Salt in the water. Okay, so some parts of your body, there will be a neutralization reaction, and that can actually change the pH of its surroundings, and that's instead of a buffer, which is going to ensure that there's no change. A neutralization reaction is just acid plus base, so any acid and any base. So today we're going to be working with hydrochloric acid and sodium hydroxide. And they react together and they give you always water and a salt. And an example of this is in the duodenum, fun word, part part of the small intestine. Part of the small intestine called the duodenum has acid-base reactions, and that's because the liquids coming out of your stomach are very acidic, and we don't want it to continue to be super acidic as it goes through your small intestine. So basically what happens in the duodenum is you've got stomach acid coming in. Your stomach has this lovely mucus lining that protects it from hydrochloric acid. Your duodenum does not. You want to absorb things, absorb nutrients in that part of your digestive system, so there's no mucus coating. So what happens is sodium bicarbonate, which is a base, is released into the duodenum, and then that acid gets neutralized. We end up with water and a salt, and then you've got a neutral or more neutral environment. This is non-reversible. So this is not the same as a buffer where it's a reversible thing. Does anyone have any questions around buffers before we move into our lab?